In the previous lecture, we have discussed the necessary condition for light amplification in a qualitative way. You have seen that actually the population inversion is the necessary condition for the light emitting from a lasing medium to be amplified. But because we have seen, according to Maxwell's energy distribution law, in normal thermal condition, the population density in the lower energy level is greater than that of the higher energy level. That is, the condition of population inversion does not involve in normal thermal condition, because you know that according to Maxwell's energy distribution law, if N1 is the number of atoms per unit volume in the lower energy level E1, and N2 is that of in the higher energy level E2, then you have seen that N1 over N2 is equal to e to the power E2 minus E1 divided by KT, and since E2 is greater than E1, so the power of this exponential is positive, and the power of exponential is positive, its value will be greater than 1. So it means in normal thermal condition, N1 by N2 is greater than 1. That means N1 is greater than N2, or you may say that N2 is less than N1. So in fact, under the ordinary condition of thermal equilibrium, the number of atoms in the higher energy level E2, which is N2, is considerably smaller than the number in the lower energy state, that is E1. Okay? And so in this condition, there will be a very little stimulated emission compared with the absorption. So definitely you have learnt that if by some means the number of atoms in the higher energy state be made sufficiently larger than the number in the lower energy state, then a stimulated emission will be promoted. And when a stimulated emission will be promoted, then you will get the amplified light. So the situation in which the number of atoms in the higher energy state exceeds the lower energy state, that is N2 is greater than N1, in fact that is called population inversion. All these things we have discussed in the previous lecture in a qualitative way, but that is without any calculation. You have seen these things in the previous lecture. But in this lecture, our aim is to discuss the same fact just in a quantitative manner, that is by the mathematical calculation. Okay? And for this, let us consider there is a lasing medium. You can see this figure. This is a lasing medium, means this is an assembly of atoms, you can say, or this is lasing medium or active medium. Okay? And let us consider that nearly monochromatic beam of light having frequency between nu and nu plus delta nu is incident on this active medium. If this delta nu is much smaller, then you can say that this incident radiation is almost monochromatic, and we can consider that the frequency which is interacting with this atomic system is nu. Okay? Now let us consider that at any distance x or at any time t, the intensity of this incident radiation is I nu. Okay? And U of nu is the spectral energy density of the stimulating radiation we consider. Then if you know that if C is the speed of the radiation in this medium, then this energy density U nu and the intensity I nu are related by this equation. You have definitely learnt this equation while studying the electromagnetic wave in electromagnetic theory. So I nu is equal to C times U of nu, and therefore you can also say that U of nu is equal to I nu divided by C. Now, if you consider that there is a width of the spectral frequency by delta nu, then this equation can equivalently written as I nu times delta nu equal to C times u of nu times delta nu. Okay. Now, as you know that if you consider that there are two energy levels, that is 1 and 2, having the atomic concentration N1 and N2, as you can see this figure. In fact, before this lecture, I have always marked the energy level by sharp lines. But this is not a real fact. In fact, there are several types of broadening effect which we will discuss in the forthcoming lecture. And due to those broadening effect, the energy levels are not sharp, but they have actually a width. So there is not a particular energy level, but there will be a energy band. Okay, so I have shown this in this figure that the energy levels has a particular width. Okay, and we consider that the photon having energy h nu is striking this lasing system. Okay, now since the energy level has finite width, so in this condition you cannot say that all of these N1 atoms in the lower energy state will absorb the photon and will move to the higher energy level. But in actual practice, it is seen that only a fraction of this N1 absorbs the photon and get transferred to the higher energy level. So let us consider that the number delta N1 out of this N1 undergo the absorption transition. We consider it. Okay. So in this condition, when we will apply the concept of Einstein's coefficient, then you can find what will be the number of transition per unit time per unit volume. That is the probability rate of such a transition you have discussed already in the previous lecture will be given by gamma 12 equal to delta N1 B12 times u of nu. Okay. But you have seen in the first equation that this u of nu is equal to I nu by C. You have seen. So this can be written as delta N1 times B12 times I nu over C. Okay. Now in the similar manner, when actually the downward transition takes place, that is the stimulated emission from higher level to lower level, then again all of the atoms, that is N2, do not get stimulated to make the downward transition. But out of this N2, you can guess that only delta N2 are stimulated for the downward transition. So in this condition, the rate of the downward transition per unit volume will be given by gamma 21 is equal to delta N2 times B21 times u of nu. And again, instead of u of nu, we will write I nu divided by C. Here actually B12 and this B21, these are Einstein's B coefficient, and you know both of these coefficients B12 and B21 are equal in value. You have learnt in the previous lecture. Okay. Now let us see. When the atom makes the upward transition, that is from the lower level to upper level, then you know that the atoms actually absorbs energy h nu. H nu energy is absorbed by the atoms. Okay. On the other hand, when the atoms make the downward transition, then for one transition, h nu amount of energy is emitted. So due to this absorption and emission of energy, there will be a net change in the energy density of the radiation. Okay. So what will be the rate of change in energy density, you can easily find it. Since due to one transition, the energy absorbed during the upward transition is h nu. So for what will be the total energy absorbed when there will be the number of transition gamma 1 2. So gamma 1 2 times h nu, that will be total energy absorbed. Okay. And similarly, when there will be a downward transition, what will be the total energy emitted? That will be gamma 21 times h nu. Okay, because these gamma 12 and gamma 21 represent the number of transitions per unit time per unit volume. Mark this. So since it is the number of transition per unit time per unit volume, so in this condition, when you will multiply these gamma 12 and gamma 21 by h nu, that is the absorbed energy per transition or the emitted energy per transition, you will get the rate of change in spectral energy density. So you can see, I have written here that the rate of spectral energy density for the spectral width delta nu, this is d dt u nu times delta nu, and that will be equal to what? This is in fact gamma 21 and you have multiplied it by h nu. So this is the total energy released per second per unit volume, and this has been multiplied by h nu. This is the total energy in fact absorbed per unit time per unit volume, and so the difference of these two actually gives the increase or decrease, that is rate of change in energy density. Okay, so I have written this d dt u of nu times delta nu equal to this much. Now this delta nu is the width of the spectral frequency. So this is a constant factor and you can divide by this factor in the RHS. So d dt u of nu is given by this much. This is h nu by c times delta n2 minus delta n1 over delta nu times bi nu. See here. Actually, you know that Einstein's these two coefficients, B21 and B12, both are equal. You have learnt it in the previous lecture. So I am not writing here either B12 or B21, but I am writing only B. Okay. You can write this B only B12 or B21, but for the sake of confusion, I am writing it only by the symbol B. Okay. Actually, here we are considering only two processes of interaction of matter with the radiation. First of all, you have considered absorption, then you have considered the stimulated emission. But as you know that in this condition, the spontaneous emission also takes place. But here in this calculation, I have neglected the radiation arising out of the spontaneous emission, because such radiations propagate in random directions. You have studied it. And as it propagate in random directions, so in general they get lost from the beam. And so I have not considered here the radiations emitted by the spontaneous emission. Okay. Now here in this equation, let us say that this is equation number 1. Okay. This is equation number, sorry, this will be not equation 1 because I have already considered 3 equations. So you should say that this is equation 4. Okay. Now, our aim here is actually to relate the intensity with the distance as the radiation passes through this active medium. So we will change this operator d dt in terms of d dx, as you have considered that the radiation is traveling in x direction. So let us consider that this radiation travels a distance dx in a very short interval of time dt. And as you know, the speed of radiation is c, so you can say that as c will be equal to dx by dt, where dx is the distance covered by the radiation in a short interval of time dt. So in this condition, you can see this dt will be what? dt is dx over c. dx over c. And therefore, when we will use this relation in the equation, in LHS of equation 4, so first of all evaluate the LHS. So d dt u of nu, what will be this? You can see this is d dx over c and u of nu. Okay, now this can be written as d dx c times u of nu, c times u of nu. But as you know that this c times u of nu you have seen in the first equation, this is the intensity of the radiation. So this is d dx I nu, d dx I nu. Okay, d dx I nu. And therefore, this equation 4 now can be written in this manner. This is di nu over dx, and this is equal to what? This is h nu over c times delta n2 minus delta n1, delta n2 minus delta n1 divided by delta nu, okay, times b I nu, times b I nu. Okay. Now let us put here, instead of this h nu by c times delta nu, delta n2 minus delta n1 over delta nu times b, let us put a parameter which is denoted by the symbol alpha nu. So this will be alpha nu I nu. So di nu over dx, this is equal to this much. In fact, here I have written this alpha nu instead of what? This has been written instead of h nu divided by c times delta n2 minus delta n1 and divided by delta nu times b, okay, times b, and say this is equation 5. Actually this quantity alpha nu is called gain constant at frequency nu. So what is this alpha nu? This is actually the gain constant at frequency nu. When you say gain constant, it means how much intensity will be gained by the radiation when it is passing through this active medium. So this is the measure of the gain of intensity, and that's why it is called gain constant. Now solving this very equation, we will relate the intensity of radiation I nu with the distance x as it is passage through the medium. So you can arrange that equation. You can see that equation can be written as di nu over I nu, and that will be equal to what? That will be alpha nu times dx. Okay. Now to get the value of I nu in as a function of x, you must integrate this equation. So integral of di nu over I nu, this will be equal to alpha nu integral of dx. Now let us take the limit of x as 0 and x. Okay, and if you consider that when distance is x, that the radiation has not traveled through the medium, it is just to enter into the medium, then its intensity is, let us say, I naught nu. We consider it. Okay, and when it travels a distance x, then its intensity becomes I nu. Okay, now you can see this will be ln I nu, and limits are I naught nu and I nu. Okay, and this is equal to alpha nu into x. When you will put the limit, what will be the result? This will be ln I nu minus ln I naught nu. Okay, and this is equal to alpha nu times x. Now you know this ln I nu minus ln I naught nu, this will be ln I nu over I naught nu. Okay, and that is equal to alpha nu times x, and this implies I nu over I naught nu. I naught nu. This is equal to e to the power alpha nu times x, and therefore you can say that this I nu, which is actually a function of x, so I am writing I nu of x, and that will be equal to I naught nu times e to the power alpha nu times x. So this equation actually relates the intensity of the radiation to the distance. As it will pass through the medium, how the intensity of radiation will change with distance, we can discuss from this equation. You can see that this intensity is varying with x exponentially, and this will increase exponentially or decrease exponentially. That actually completely depends on the value of this alpha nu. That is, alpha nu is either positive or negative. That will decide that the intensity will increase or decrease. So you can see from that figure, if this alpha nu is greater than 0, that is positive, then what will happen? Then actually the intensity will increase with increase in distance. I nu will increase with x. Okay, and if alpha nu is less than 0, that is negative, that is positive, you should say here, that is negative, then I nu will decreases with x. So now we will see when this I nu will be positive and when it will be negative. You will see just now that when there is a population inversion, that is when N2 is greater than N1, then you will see that actually this alpha nu will be positive, and you can say that intensity will increase exponentially with the distance x as the radiation passes through the medium, and we get a highly amplified beam of radiation. But if there is not a population inversion, that is N2 is less than N1, then you will see that this alpha nu will be negative, and with increase in distance, the intensity of radiation will decrease exponentially, and we finally get a highly attenuated beam or no beam. Okay, but let us decide it. Actually, you know that the energy levels E1 and E2 have finite widths. So the spectral line due to the transition between these two levels has a finite frequency spread, that is delta nu, about a mean frequency nu naught. Okay. So we can estimate this gain constant alpha nu at this mean frequency, and for estimating it at this mean frequency, we have to put delta n equal to n. So let nu naught equal to mean frequency. Okay. So at the mean frequency, this delta n will be equal to n, and this implies that delta n1 will be equal to n1 and delta n2 will be equal to n2. Okay. So in this condition, the gain constant alpha nu, I am writing it alpha nu 0 to signify that this is the gain constant for the mean frequency. Okay. Then what will be this? This will be, as you can see, the expression for this gain constant here in this equation, equation number 5. So in this equation, nu will be replaced by nu naught, delta n2 and delta n1 will be replaced by that will be replaced by what? N2 and n1. So what will be the expression for the gain constant at the mean frequency? You can see this will be h nu naught by c times n2 minus n1 divided by delta nu times b. Okay. So now you can see that this equation actually implies that if n2 is greater than n1, then this alpha nu naught will be positive. You can see it will be positive. And if it is positive, you have learnt here that then I nu will increase exponentially. I nu increases exponentially. Okay. And when there will be an exponential increase in intensity, what does it mean? In fact, in this condition, the intensity will increase with increase in x, and we get a light beam progressing through this medium with increasing intensity at a high rate, because exponential increment is very high, and so there is an amplification of the intensity of light. So you can see that this population inversion, that is n2 greater than n1, is the necessary condition for light amplification. This thing we have already discussed in the previous lecture, but here mathematically you can see that if n2 is greater than n1, then this gain constant is positive, and if gain constant is positive, then the relation between the intensity and the distance implies that the intensity of the radiation will increase exponentially as the radiation passes through the active medium. Okay. So in this condition, you can see, if you will plot the intensity of the radiation in against of this distance x, this I nu of x has been plotted, then when this x, the formula is what? This is I nu of x. You can see this is I naught nu times e to the power alpha nu of x. Now, alpha nu is positive, and in this condition, when x is equal to 0, then this I nu will be what? I nu 0 will be equal to simply I naught nu, because this exponential factor will be e to the power 0, and that will be equal to 1. And with increase in x, it increases very rapidly in this manner. This is the value of I naught nu. But at the same time, you can see from this result that if the situation is not like this, that is n2 is not greater than n1, but n2 is less than n1, then from this equation 6, you can see if there is no population inversion, that is n2 is smaller than n1, then what will happen? Then you can see that this alpha nu naught will be negative. And if it is negative, then you know that intensity will decrease exponentially. Then I nu decreases exponentially. With distance x. Exponentially with x. It means in this condition alpha nu is positive for in this figure, and if alpha nu is negative, then what will happen? You can see if you plot here the I nu in against of x, then at x equal to 0, intensity is I naught nu, and with increase in distance it will decrease exponentially. So finally, after this discussion, I hope you have understand that the population inversion is the necessary and essential condition for light amplification. Okay, so when we make a population inversion, that is the population density in the higher energy level is greater than the lower energy level, only then we get a highly amplified laser light from the lasing medium or the active medium. Okay, I hope you have understand each and every step clearly.